Thank you, Paavo and Jan, and I'm delighted to hear about the idea that Bohm himself was a pragmatist. It reminded me, if you'll forgive a little bit of self-advertisement, the next time I'm giving a talk in this building next May, I'm actually talking about a pragmatic view of causation with some connection with retrocausality, because I'll be talking about Dummett, among other people, who's the most distinguished philosopher, to the person who in the 1950s and 60s sort of cleared up a philosophy of retrocausality and made possible its application in quantum mechanics in a conceptual sense. So, and thank you too for inviting me to this remarkable meeting. I think I can say that this session in particular is historic. I'm pretty sure that there can't have been another occasion in the 2,000-year history of this city when a group of people spent an entire Saturday morning talking about retrocausality. So we're really on new ground here. Okay, so let's start with some familiar ideas. In 1935, Einstein, Podolsky, and Rosen argued that quantum mechanics must be incomplete. Their argument assumed that there can be no influence from Alice to Bob as we now represent the kind of experiment that they were discussing. Why could there be no influence? Because there's no such thing as action at a distance. You'll see in a moment why I'm distinguishing the principle I'm calling no influence from no action at a distance. This seemed uncontroversial. As Schrödinger said, that year measurements on separated systems cannot directly influence each other. That would be magic. And then in 1964, Bell argued that no local, that is, for my purposes, no hidden variable theory without action at a distance is compatible with the quantum predictions in these cases. Now, as we've already seen at this meeting, there's still some argument about exactly what Bell's results proved, but a common reading, for example, Tim Maudlin's, is that Bell showed that the quantum world is unavoidably non-local, that is, violates the principle of no action at a distance. So in some subtle sense, on this reading of Bell, the argument shows that there is action at a distance from Alice to Bob and vice versa. Here's a little piece of text reflecting this view from a piece in the Scientific American by David Albert and Riva Galchen. They say quantum mechanics has upended many an intuition, but none deeper than locality. And this particular upending carries with it a threat as yet unresolved to special relativity, a foundation stone of our 21st century physics. Okay, but as we saw in assuming no influence, Einstein, Podolsky, and Rosen had relied on what's in effect the principle of no action at a distance. And in the late 1940s, a Parisian graduate student, shown here with his advisor, Louis de Broglie, spotted a loophole. He saw that Alice's choices could affect Bob's particle and vice versa without action at distance if the effect followed a zigzag path via the past. This man was Olivier Costa de Beauregard, who passed away almost, 10 years ago now. A couple of years before that, I had the opportunity to meet him. I went out with Guido Bacigalupi and we had lunch with him at his house south of Paris. And here's a diagram from one of his papers on the subject. This one, he first published in 1953. Actually, I asked him when he first had the idea, and he said he first had the idea in the late 1940s, but for several years de Broglie wouldn't let him publish it because de Broglie thought it was too crazy. And then when Feynman published his work on positrons being electrons going backwards in time, de Broglie said, he relented. He said, well, look, there's this clever young American publishing these ideas. Perhaps you should publish yours. And here's a diagram from one of the later papers. Costa de Beauregard says of this space-time diagram of the Einstein paradox, the correlation between L and N is tied through C in their common past by the Feynman-style zigzag made up of the time-like vectors CL and CN. So there's the zigzag, and there's Costa de Beauregard calling it a zigzag. It's the idea that in these apparently non-local cases in quantum mechanics, the influence is mediated locally via the past. So everything stays on the light cones. Now, originally, this was more than 10 years before Bell, and Costa de Beauregard thought of it as an objection to the EPR argument, because it undermined the case for no influence by showing that you could have influence without action at distance. But it kind of undermined EPR's conclusion, because the zigzag isn't there in standard quantum mechanics, so if you put it in, you're accepting that quantum mechanics in its standard form was incomplete. But the interesting application of it is the one that is possible once we have Bell's result, and it's the idea that it may be the key to saving no action distance in the face of Bell's theorem. So Bell's argument assumes that Alice's choice of measurement setting doesn't affect the prior state of the photon, and the same for Bob. So it assumes that the measurement setting that Alice chooses here doesn't affect the state of the photon in that region. And the Bell correlations are easy to explain in principle if we allow such retrocausality, that is, if we allow the Parisian zigzag. And so we can save locality, that is, the principle of no action distance, and the tension with relativity vanishes. So that possibility has been there right from the beginning. And obviously, Bell knew it was there. So why isn't the Parisian zigzag more popular? Well, here's Bell's own answer insofar as I know what it is. In the late 80s, I wrote to him and sent him copies of a couple of my papers, early papers on the subject, and he kindly wrote back, and this is the relevant section. He says, I have not myself been able to make any sense of the notion of backward causation. When I try to think of it, I lapse quickly into fatalism. Now, I think it's not entirely clear what he had in mind there, and I'll come back to it a little later if I have time. But before that, I want to give you what I think is a new argument for retrocausality in quantum mechanics, which could in principle have been discovered long before the EPR argument. I want to say that what I'm going to give you is a sort of crude first model of this argument, the one that I came up with coming out of joint work I was doing with Ken Wharton. The argument has now been generalized in an elegant way by Matt Leifer and Matt Pusey, and so if you want the sophisticated version, you can go to their paper. But their version, I think, relies on some of the ideas that I'm going to introduce here. So I'll give you the simple version. What we're going to do is to compare classical and quantum polarization. So this is the classical case first. Here's a classical polarizing beam splitter. We've got a beam of polarized light with polarization tau coming in from the left. It hits the beam splitter, which has an angle sigma r, and it's split into two beams, the intensities of which are given by Marlis's law. So the transmission beam has intensity cos squared of the difference between the angle of the polarization and the crystal, and the reflection beam has the intensity sine squared of the difference between those angles. Here's what we can think of as the time reverse case in the classical theory. The classical theory is time symmetric. In principle, you can do the time reversed experiment where you use a polarizing beam splitter to combine two beams of different intensities to produce a single output beam. Of course, you need to get the phases lined up so that the other output beam is completely cancelled. But in principle, because it's time symmetric, you can do it. And it's governed by the time reverse version of the same equations. Okay, now let's put the two parts, the two things together in that way. And I want to say two things about this combined experiment. One is a comment on the role of the polarization here. And it's very natural to think of the polarization as a local mechanism, as the thing that carries information from one side of the experiment to the other. I mean, in normal circumstances, it's easy to think of how you could use this as a communication device or a control device. And the thing that would be changing if it was used in that way is the polarization in between. So in the normal sense, it's the polarization, which is the local mechanism that bridges that gap. That's just a way of sort of pumping your intuition to take the polarization seriously, as what in the quantum case Bell called it beable. Now we're going to be thinking about what we can control if the only thing that we can control is one of these angles, sigma L or sigma R. That is the setting of the polarizing crystals. So we're going to be looking at the case where we can wiggle that setting, and the case where we can wiggle that setting. Okay, so treating the case on the left first, suppose we can control the left polarized angle sigma L. I put the knob on the picture so that we can see what we are controlling, as it were. But we don't control these input beams. The input beams are controlled by a creature I'm going to call the demon of the left. Here's the demon of the left. The demon of the left shares with us the desire to get a single beam coming out there. So whatever angle we set, there's some choice of input intensities which will guarantee that there will be such a beam. So given that we know this is the demon's intentions, and we know that the demon knows his physics, as it were, we can be sure that a beam will come out. The question is, and the demon, as you can see, the demon can see our choice of measurement setting there. The question is, who controls the polarization of that output beam? Is it us, or is it the demon, or is it somehow a mixture of both? Do we both have some control? The answer turns out to be, it's not hard to see this, that the demon has complete control. The demon can make tau whatever he likes by choosing appropriate input intensities, given that he knows what the setting is. So, you see there I'm making a change to sigma L, but as you can see, the polarization isn't changing. The reason, although it's not shown on the diagram, is that as I change sigma L, the demon is making corresponding changes in the input intensities, and so the polarization of tau isn't changing. What's interesting about this demon, the reason he's been designed like this, is that what he does is exactly what nature does on the right here, in the original version of the experiment. So suppose now that we just control the right polarizer angle, but not the output beam. Here's nature represented as sort of a gesture ahead to the quantum case as a cat the size of a bus to represent the sort of macroscopic case. Can we control the input polarization, tau? Well, in this case, it seems to us that the answer must be blindingly obvious. Of course not. So if I make a change there, nature absorbs the change in a difference in the output intensities, and the polarization doesn't change. So there's no retrocausality here in the classical case. Okay, that's the classical case. Here's the quantum case. We have a quantum version of Marlus's law, which is where instead of the intensity, we now have a probability for the photon being found on that path or on that path. Again, we have a time-reversed version of the experiment with, if we're careful about what we mean by probabilities, then we can again talk about an expression of that kind. And again, we want to look at the combined experiment of this form. Again, it's sort of intuitive to think of the polarization as a local mechanism, given that in the normal case where we have control over the inputs, we can use a device of this kind to signal.
Could you say again what's the difference to the previous example?
This one is quantum, that was classical. So this is a quantum polarization, and intuitively it's just whatever beable connects changes on the left to changes on the right. Now, I'm going to use the assumption that there is such a beable. I'm going to call that assumption realism. And again, we're going to be interested in what we can wiggle if what we can control is just the polarizer settings. So let's consider the case on the left, and again, we're considering the case where we just control the left polarizer, but the demon of the left controls the photons on the input beams. Question, can we control tau L, the polarization? But remember, in the classical case, we saw that we couldn't. The demon had complete control there. In the quantum case, it's different so long as we impose an additional restriction on the demon. So as long as we require that the demon has to feed the photon on one channel or the other, the demon's not allowed to feed in a superposition of the two, then under those conditions, sigma L has to be either, tau L has to be either equal to sigma L or equal to sigma L plus pi on 2, depending on whether the demon puts the photon on one channel or on the other channel. I'm going to call the assumption that the demon has to put the photon on one channel or the other the discreteness assumption. So under these conditions, given the discreteness assumption, we can't fix the polarization completely, but we can restrict it to just two possibilities. And that's a whole lot more control than we had in the classical case. And where it's coming from, obviously, is from discreteness. Because the discreteness ensures that the demon only has two options available. We've got this continuously valued variable, so the demon just doesn't have enough options to counteract the changes that we can make here. And so if we represent this possibility that the polarization can be either in one direction or at right angles to it, then you can see how, as I change the polarization, I'm changing what, given the assumption realism, is a real property of the photon. So under these conditions, given discreteness, we have a degree of control in the quantum case that we don't have in the classical case. But of course, that's forward causality. But now let's look at the case on the other side. Again, suppose we control the right polarizer, the setting sigma R, but not the output beams. Nature controls them again. Question, can we control some property, and now call it tau R, of the incoming photon? And the answer is yes, provided we give ourselves two further assumptions. Well, one assumption is the one we already imposed on the demon, the discreteness assumption, that nature has to put the photon on one channel or the other. The other is an assumption of time symmetry. This is, roughly speaking, this is the assumption that if tau L exists, governed by rules on this side, then the time reverse version of those rules will guarantee that TR exists. I mean, you think of this intuitively as the principle that if we viewed a video simulation of the ontology at an experiment of this kind, we shouldn't be able to tell whether the video was being played forward or backwards. And if we didn't have tau R in the ontology, we'd be able to do that. So in this case, given time symmetry and given the discreteness restriction on nature, we get the same kind of control on the right of tau R as we had on the left of tau L. So in this case, you see, as I change sigma R, I'm changing some property of the photon before it arrives at that polarizer. So
does discreteness mean here you can't have a superposition afterwards?
Yes, good. Yeah, and we'll come back to that. Yes, and so, but it also means, and just to jump ahead a bit, it also means that the the ontology can't be something like a Bohmian ontology, because in the Bohmian ontology, you've got the option of absorbing the wiggle in the wave function, as it were, even if the particle actually comes out on. Okay, so there's room for discussion here about the precise content of all of these assumptions. But as it were, modulo that uncertainty about the precise content, what the argument seems to show is that the combination of realism plus time symmetry plus discreteness implies that you have retrocausality. And the structure of the argument is that the discreteness shows you have a kind of forward causality in the quantum case that you don't have in the classical case. And given time symmetry, you must have that backwards as well as forwards. So that means that we've got a choice. We have to reject at least one of the principles on the left, or we have to reject the principle that causation only works forwards. So what are we going to do? Let's ask the man in the street for some advice. This is the man I have in mind. It's the wrong street, because this is the man in about 1932, and we wanted to get to him sort of just after 1905, when he's realized that light comes in little packets, we now call photons, because I think the argument as presented here doesn't rely on anything which wasn't available already at that point. So how is he going to respond to this question? Which one of these things should go? I think he's going to want to hang on to realism. I put a little question here, and this is partly, the question mark is partly inspired by what I've learned from Matt Lee from Pusey's paper about what my assumption of realism actually comes to, but we can come back to that if we have time. Seems pretty clear he's going to accept time symmetry. In 1909, 1910, he has a famous discussion with Ritz in which he makes it clear that his intuitions are that time symmetry is fundamental. He's presumably going to accept discreteness, because one of the great discoveries, I think the one he regarded as the greatest of his discoveries in 1905, was the sort of discrete nature of light. But that means that he's going to have to give up the assumption that we can't affect the past. I think there's an interesting comparison with Bell's theorem here. So as usually formulated, Bell's theorem says something like the principle of no action at distance plus an assumption which is called something like independence, which from my lights looks like a no retrocausality assumption. That implies something incompatible with quantum mechanics. But we can rewrite an argument of that form so that it says that quantum mechanics plus the assumption of no retrocausality implies action at distance. Or to use the Schrödinger terminology, it implies magic. Or rewriting it again, that means that quantum mechanics plus no magic, that is no action at distance, implies retrocausality. So of course, that's the way I've always wanted to read Bell's theorem. And when people say to me, but does this retrocausality stuff have any experimental consequences? And of course, I point them in the direction of Aspect and other experimental experimental confirmations of the Bell correlations. So reading Bell's argument in that form, then the new argument I've offered you can be written in that form with realism presupposed. And the interesting thing is that this bit, the quantum bit, is really essentially the same thing in both cases. And one way to see that is to use a little diagram like this. So what we've got here is a space-time diagram of an EPR Bell experiment done with photons and polarizing beam splitters. And we're standing this diagram on top of a mirror so that we can see the reflection of the left-hand side of it. And if you just look at the reflection of the left-hand side, combined with the right-hand side, then you've got a space-time diagram of the one-photon experiment, the time-like one-photon experiment that we've been considering. And this reflection isn't some kind of trick. On the contrary, it reflects a deep symmetry in the path integral. So I've changed Alice's name to reflect the reflection. So Alice is now called Aquila down here. That's Alice backwards. But this sort of half-reflected version of a Bell experiment is just the one-photon experiment we've been discussing. And what we saw is that with this restriction on the inputs here, a restriction whose effect is just to make the inputs here look exactly like the outputs up there, so that the reflection is a valid one. We saw that in that case, the case we described as having the demon, Aquila has an influence on the polarization here, and hence on Bob's probabilities of outcomes given settings, even if she doesn't control the input channel. That was the new kind of influence that comes from discreteness. And by the symmetry represented by the mirror, Alice has the same kind of discrete control over Bob's probabilities, at least epistemically speaking, and Bell shows us that no ontic model can avoid it. So I think, and again, this is something which was clarified for me by the Leifer and Pusey paper, I think that there's a sense in which the argument that I gave you at the beginning relies on exactly the same mathematics as the EPR and Bell arguments, just presented in a new way. And what the takeaway message, I think, is that discreteness or quantization is playing essentially the same role in both cases, but the different geometries are producing different bads if we ignore retrocausality. So if you ignore retrocausality in this case, you get action at distance. If you ignore it in this case, you get time asymmetry. So different bads, but fixable in the same way. Okay, that's it. How am I doing on time? Good. Okay, so I can do the little additional section. Now, one of the responses that people, those of us who like to think about retrocausality in quantum mechanics get is what I'll call the is science safe argument. Here it is from a nice survey paper by Howard Wiseman. Where's Howard? Oh, there's Howard. I particularly wanted to get to this because both of my targets are here today. I've rearranged Howard's text a little bit, so the numbering is not Howard's, but the bits in between the quotes is certainly Howard. So Howard says, to be scrupulous, this is in a footnote in this survey paper about Bell's theorem, to be scrupulous, there are other ways that the correlations in an EPR Bell experiment could be explained away. One could entertain the idea of backward in time causation. 2, one could deny that the experimenters have free will to choose the settings of their measurement devices at random as required for a statistically valid Bell experiment. Howard says, I do not consider these escape routes because they seem to undercut the core assumptions necessary to undertake scientific experiments. So the suggestion is that there's something deeply unscientific about the retrocausal proposal. Okay, so that's Howard. The other is Tim, whereas Tim is down here, conveniently in a straight line with Howard. That's a nice bonus from my point of view. This is from a more recent paper by Tim, in which, among other things, he's talking about a nice example given by Schrödinger in 1935. Tim says, there's the so-called idea of superdeterminism. Recall Schrödinger's class of identically prepared students. If you don't know this example, I'm not going to explain the full thing to you, but the takeaway message is that Tim is presenting here what I call the retrocausal option and the predetermination option, and is claiming that both are incompatible with the scientific method. So recall Schrödinger's class of identically prepared students. we're told that they can all answer any one of a set of questions correctly, but that each can only answer one and then forgets the answers to the rest. It's an odd idea, but we can still test it. We ask the questions at random and find that we always get the right answer. Of course, it's possible that each student only knows the answer to one question, which always happens to be the very one we ask. But that would require a massive coincidence on a scale that would undercut the whole scientific method. All right, well, retrocausalists want to say, no, all it requires is that our decision as to which question to ask has a retrocausal influence on which piece of the syllabus the student studies. And then Tim presents the other option, the superdetermination option. Or else we're being manipulated. Somehow we're led to ask a given question only of the rare student who knows the answer. So when we switch our method of choice, handing it over to a random number generator, or the throw of a dice, or to be determined by the amount of rainfall in Paraguay, but maybe all of these have been somehow rigged too. Of course, surely such a purely abstract proposal cannot be refuted, but besides being insane, it too would undercut scientific method. All scientific interpretations of our observations presuppose that they have not been manipulated in such a way. And on that point, I agree completely with Tim. But I don't agree about the retrocausal option being non-scientific, quite the contrary. So it's the first option that I have in mind, the one I labeled 1 in the quote from Howard, not the option that has our choices of measurement settings being controlled in some way. But contra Tim and Howard, I think that science is very comfortable with massive coincidences between our free interventions and other events. We have a name for it, we call it cause and effect. In effect, the scientific method is going around in the world, wiggling things, and looking to see what else wiggles, looking for those massive coincidences. That's what looking for causal structure is. And the point about these retrocausal models is that they suggest that sometimes when we wiggle something, what wiggles is something in our past. Otherwise, it's just the standard scientific method. Here we need to postulate that it can sometimes work backwards, but science doesn't tell us that that's impossible. And if you sort of affirm that it's impossible and refuse to consider it, you're not defending science, you're being anti-scientific in allowing a piece of folk metaphysics to get in the way of the application of this procedure of wiggling things and looking to see what else wiggles. Now, in this case, of course, you can't literally look to see what else wiggles, because for consistency, the thing that wiggles has to be sort of, as it were, out of sight of direct observation. So it has to be theoretical reasons, reasons of symmetry, reasons of avoiding no action at distance, that tells you that makes you interested in models in which something is wiggling in the past. But it's, I mean, that's true of many other cases as well, as other people have already said at this conference. And moreover, as the argument I gave you shows, the kind of backward causality that we turn out to need for the Parisian zigzag is extremely subtle. It's so subtle that until it's pointed out to us, we don't realize that there's this subtle kind of forward causality which is present in the case of quantization, but not present in the classical case. In fact, it's even more subtle than that, because that little bit of forward causality that we get when we have the demon, that's enough to explain the correlations all by itself. And if we had retrocausality, then we could presumably do it with something even weaker, because we'd, as it were, have influence from both directions to work with. So the moral here is that this kind of scientific panic at the idea of retrocausality is entirely hyperbolic. We should just, calm down, put our scientific hats back on, and investigate the advantages of models that incorporate retrocausality. So there's my conclusion in response to this argument. And that's the end. Oh, this is, I should say about this picture, this is a cafe in Paris. I like to think that, at least in Paris, Costa Beauregard's idea is so well recognized that they've named this establishment after it. And these are some papers. That's the one in which I present this argument. That's one of various pieces that Ken and I have written together, or a couple of them. And this is the Leifer and Pusey argument that I mentioned. Thank you.